Hello, everyone, and welcome. So today we'll be going over measures of association. And this recording, how I'll be doing it is instead of having a full screen view like this one, I'll do the lecture recording on this screen because for a couple of initial slides, I want to go back and forth, and it's easier when I have them at the side. All right, so I'll be doing this recording on a normal PowerPoint mode rather than a full screen PowerPoint mode. And one more housekeeping before I begin. You will see that couple of my recordings with the title slide, they haven't been updated. So over here, you may see 2020 or something like that. But obviously, the content is updated each year. All right. So don't mind about the title slide. I just took out time yesterday and I updated all of my title slides. Okay, so don't mind if I have 2020, 2021 or whatever. These are the latest recordings. So you're getting the most relevant and recent content. Okay, and one more housekeeping is that in my recordings, you will see all of these various highlights. Why do I have these sort of highlights? It's because it helps me to focus on what I think is important when I'm talking, because I don't read out of my slides. All right, so you may have already noticed that. I don't do newspaper sort of a recording where everything is like I have a transcript in front of me. That's not how I record. It's like over here and it's coming out, and these points, these concepts, they help me guide and steer my dialogue and discussion for the lecture. All right, so my recordings will have these highlights, but when I upload it on your Canvas, these slides that I upload on your Canvas, I'll make sure all of these unnecessary highlights are removed, because these highlights are basically to help me to focus on things and to have a proper direction when I'm narrating a lecture to you. All right, because I don't have a transcript, and it's just these points that help me to make up the discussion. All right, guys. So what does measures of association mean? It means that you have an independent variable, you have a dependent variable, and you want to link these variables together, your IV and your DV. This is essentially measures of association. All right, so that is what you're trying to do. You're trying to make links between your IV and DV. This technically is called as measures of association. In prospective cohort studies, what are these type of studies? These are longitudinal studies. Maybe you are following participants for 5 years, 10 years, 50 years. These sort of prospective cohort studies, the most common measure of association that is used is risk ratio. And I'll also be talking about attributable risk. But I have to emphasize and highlight that 99% of the papers that you come through, which are prospective cohort in nature, they will be citing risk ratios, because risk ratios is the most common and yes, the most important sort of an association that we use when we want to find links between our IV and DV in a prospective cohort study. All right. And what else you will be learning today? You will be learning about using measures of association such as odds ratio and attributable fractions. Again, in this, you have a winner, which is odds ratio is the most common, most popular one, which is cited in 99% of the papers. All right. And which sort of papers will use odds ratio? Research or study designs such as case control design, cross-sectional designs, they will report in terms of odds ratio. All right. So when you want to make an association between your IV and your DV, but in a cross-sectional study or a case control study, then the kind of calculation that you will be doing is odds ratios. All right. So attributable risk and attributable fraction, guys, this is not really that popular. This is not very common. You may find it in few governmental reports here and there. But what is well established and the most common indicator of association that is used is your risk ratio and your odds ratio. All right. Why am I saying this? Is because this is what you will encounter in a lot of your papers across your health faculty, all right, be it physio, nutrition, public health, so on and so forth. Then we'll be touching base on the concepts of validity and reliability. And then we'll be looking at threats to validity and reliability. Very, very important concepts, guys, especially when you're doing your own research. That is why I'll try to take examples from my research here and there so that you can understand what does validity and reliability mean in real life research. Okay. Again, guys, please appreciate that a unit such as epidemiology is a theoretical unit, all right? Meaning it is, before you learn to apply anything, you need to learn the theoretical foundation of that subject matter. So before you learn how to do research and you start dealing with people and data sets and doing all these big things, you need to study the fundamentals, all right? So for example, all of us studied ABCD. It was really boring, all right? But why did we study that? Only because we studied ABCD. Now we can apply ABCD, meaning we can make sentences and phrases and whatnot, okay? And we can, facilitates communication, all of that, all right? So all of that is application in terms of language, but you learn the basic alphabets first, which is ABCD. So epidemiology is the ABCD of research, okay? So a lot of students jump into this course and they are like, oh, okay, so now what do I start doing? No, first you are learning the theory. First, just understand the theory, and then depending upon what research you do in the future, you will apply one or two epidemiological concepts in your research. There is no one gold standard research out there, guys, where you can apply all of these 13 weeks of concept in one research. That's ridiculous, all right? That's why EPI is a theoretical subject. It is teaching you the theory of various sort of concepts which are related to research. And then when you do your own research, you apply these theoretical concepts, and these theoretical concept in practice makes a lot more sense and a lot more meaning, okay? So please do appreciate that although we are practicing, a few practice-based examples, case studies, which is all well and good, but the genuineness of epidemiology comes when you actually start doing your own research. Then it all makes a lot more sense. Okay, so those are the few important points that I wanted to cover, and that is basically your real life application. Okay, so now we'll move on further. A few YouTube videos to give you a feel of what is odds ratios, risk ratios. Now, now moving on further. So as I said, what does measures of association mean? It means when you are trying to link your IV and DV, when you're linking your IV and DV, which are studied in a prospective cohort study, all right, you use risk ratios, which is the most popular one, most common one, and the less popular one, which is not really used in today's time as much as risk ratio, is your attributable risk. Now, you have to understand that in prospective cohort study, what happens, guys, is that you have a true incidence, all right? You know the true incidence, meaning you're following people for 10 years, and then within that span of 10 years, they develop diabetes or heart attack or hypertension or cancer or whatever it is, okay? So basically, you know when that disease condition happens. So that is true incidence, okay? So whenever you have the ability to calculate true incidence, then when you try to link your IV and DV, this relationship or this association is termed as risk ratio. So remember, risk ratios or attributable risk ratios or attributable risk are calculated when you have prospective cohort studies. In prospective cohort studies, you can identify and you can know the true incidence because people develop the health outcome, the disease condition during the course of your study. Okay. So yeah, those are the most important points for risk ratios. So don't mind if I keep undermining attributable risk and I just keep on using the term risk ratio, because I want you to register that this is what you'll most commonly see in research papers. And just to say, share that with you, let me share this. So I'll just minimize this, and I'm still sharing this screen. I'll just be very sure, yes, just to be sure that I'm sharing the right screen. So guys, if you see this paper, so this paper is a meta-analysis which I published only last year. This systematic review and meta-analysis is on prospective cohort studies. Okay, so the title of the paper is, the title of the paper is this. So it's a prospective cohort study. All right. I don't know why it's all so funny. Hang on. Okay, yeah, you can cite the article as. So if you see, it's a systematic review and meta-analysis of prospective cohort studies. So what did I tell you about prospective cohort studies? You generally calculate risk ratio, which is what you'll be seeing in the literature. Why am I citing this research? Because it's a very, very recent meta-analysis and systematic review of prospective cohort studies, only published in September 2021. And then if you see what has been calculated, so if we look at the abstract is over here. Yep, the abstract is over here. So now if you see, guys, everywhere you will see these RRs, risk ratios. RR is risk ratios. Everywhere I have calculated risk ratio. This is a very big study. It is summarizing 79 other prospective cohort studies. So a systematic review and a meta-analysis, and you will learn that later, but you have learned study designs, all right, and the type of research articles. So this systematic review and meta-analysis is a collation of 79 prospective cohort studies. I was able to calculate risk ratios. Why? Because 79 of these studies reported risk ratios, and therefore I could derive a common risk ratios out of all of these studies. All right. So what am I trying to emphasize is that when 79 studies are using risk ratios in prospective cohort study, meaning that is the most common, say the type of association which is undertaken when you are trying to make an association between IV and DV in prospective cohort studies. Okay. So I hope this has added a little bit of real life context to it. All right, so that is about your risk ratios. Similarly, when you have case control studies, cross-sectional studies, the most common one which you use is odds ratio. Yes, you have something called as attributable fractions, but again, not very commonly used. Odds ratios is the most popular one which is used. Now, in cross-sectional studies, case control studies, you need to appreciate that you can never know the true incidence. All right. Why? Because in a case control study, maybe you have your say your study is on smokers versus non-smokers and their association with lung cancer. Okay, so now in this condition, people are already smoking, and then you have non-smokers. So you don't know when they started smoking and things like that. All right, and when would the outcome be developed? Okay, so you're just seeing that if these smokers have lung cancers versus a healthy population which may or may not have lung cancer. All right, so over here you don't know the true incidence rate. Again, with cross-sectional study, you have the same issue. What are cross-sectional studies? I just have 1 month for data collection. This is a snapshot. I'm not following people for 10 years or 5 years or 2 years. All right, I just have 4 weeks for data collection. I am measuring these participants once, and that's about it. Okay, so that is a cross-sectional study. It's just a snapshot. So now in these sort of studies, when you cannot identify the true incidence, that is when the association which you calculate between IV and DV, this association is termed as odds ratio. Okay, so risk ratio is for your cohort studies and your odds ratios is for your case control studies, cross-sectional studies. Okay, so I hope this has made more sense now. All right, so we'll be looking at, so in this chapter, you have a total of only 4 calculations. Risk ratios, attributable risk, odds ratios, and attributable fractions. That's about it, just 4 calculations. Okay, so we'll see now how to calculate them. Now, guys, the only difference between risk ratios and attributable risk is the formula. All right, so in risk ratio, you have your exposed group and your unexposed group. Exposed group is the group which is having the disease, the health outcome, and unexposed group is the group which is not having the disease. All right. So disease group versus disease-free group. All right. You are comparing these two groups by dividing them. Okay. So the formula is by dividing them. All right. So it's and now if we look at attributable fractions, let me go on to that first before I say anything else. So this is the formula for attributable fraction. Over here, you have the same concept. You have two groups. One has the disease, one does not have the disease, meaning one is exposed to the disease, one is not exposed to the disease. Here, you are comparing the group by identifying the difference between the group. Okay. So if you see, essentially, what will it give you? It will just give you a different way of saying things, but the concept is similar. You have your exposed group, you have your unexposed group. You are comparing these groups. In one formula, you are dividing them, and in one formula, you are finding the difference between these two groups. That's about it. Okay. And as I said, the most common and the most popular thing to do is to calculate risk ratios. So how are researchers calculating risk ratios? By dividing the group, by dividing the exposed group to the unexposed group. Okay. So basically, this is what it is. It is not wrong to calculate attributable risk. It is not wrong to calculate risk ratios. It depends upon your research question. How do you want to compare them? Most of the researchers, they compare these groups by dividing them. Very rarely, you may compare the groups by subtracting them. All right. So it depends upon your research question, how you want to frame your hypothesis, how do you want to interpret your findings, that you may use this. But yes, the most common one which is used is risk ratios. Okay. So yes, when your risk ratio is equal to, so 1, what does it mean? It means equal rate of, say, the health outcome in both of the group. Greater than 1 indicates increased risk in the exposed group. Less than 1 indicates decreased risk in the exposed group of the health outcome or the disease. Okay, so now this will make more sense when we look at an example. All right, so now this is the example. So now remember, risk ratio, division. All right, attributable risk minus. Okay, concept same. You're just comparing two groups. All right. So yeah, in risk ratios, now let's look at this example where you have people who have gone to the church. All right. So some people have gone to the church on Saturday. Some have gone to the church on Sunday. All right. And maybe they had, say, afternoon tea or something like that over there. And then some people experienced food poisoning and the others did not experience food poisoning. All right. So we have people who went on Saturday. When people went on Saturday, 20 of them had food poisoning, 55 of them did not have food poisoning. If there are people who go on Sunday, all right, so of people who went on Sunday, 5 of them experienced food poisoning and 55 of them did not experience food poisoning. Okay. And this is the total. So you have 75 people, say, visit, say, the church on Saturday, of which 20 of them had food poisoning. You had 60 people visit the church on Sunday, and you have 5 people who experienced food poisoning. Now we know the formula is by dividing. Okay, so exposed group and versus the unexposed group. So which one is the exposed group over here? You have Saturday. They are a greater number of people who are exposed to this. Okay, so the exposed group is your 20 divided by 75. And then your Sunday, you have 5 divided by 60. Okay, and then this is what you get. It's as simple as it is. And then finally, you end up with 3.4. So what does this mean? Like, how would you interpret this in words? The risk of food poisoning was 3.4 times higher among people attending church on Saturday in comparison to Sunday. Okay, so this is as simple as it gets. It's a formula where you're comparing groups by dividing them, exposed group versus the unexposed group. Okay. All right, so that's about it with the risk ratios. Okay, now attributable risk. So now attributable risk, as I said, that attributable risk is when you do that, when you're trying to find out the difference, all right, between the incidence of disease in the exposed group versus the unexposed group. Okay, and basically, what does this mean in real life settings? So, for instance, with attributable risk, say you may be able to say, this is how you may be able to term the findings. So for instance, one study, like, for example, there are, yes, there are many causes of lung cancers which are out there, all right? But one of your study showed that the attributable risk for cigarette smoking, all right, and lung cancer was 85, all right? Why am I reading this out? So that you can pay attention over here. What does this mean? This means that 85% of lung cancer, all right, the disease cancer, the health outcome cancer, are attributed or attributed. What does the word attributed mean? It means caused by, or like, because of, all right? So are attributed to cigarette smoking. Okay, so that is how the result can be termed. All right, then you may have, say, some other study, and they may show that cigarette smoking as a cause of lung cancer was only 15%. So what does this mean? It means that in this second study, in this population, cigarette smoking is responsible for only 15% of lung cancer, meaning there are many other variables out there which are responsible for people getting lung cancer in study 2. Okay, so this is what it means. All right, so this is how basically you can say understand the difference. Okay, so now over here the formula is again very simple. Attributable risk is where you have your exposed group and you have your unexposed group, and you are minusing them, okay, subtracting them. So now what is the formula looking like? Again, the same example, so it helps you to, like, understand the concept. So again, you have people going to church on Saturday versus Sunday, all right? And these are the same numbers as before. Now what you're doing is the first thing which you do is you for attributable risk. All right, so first you have to calculate the risk ratios over here. So it is the same thing. You had 20 divided by 75, 5 divided by 60. So if we look over here, okay, 20 divided by 75, 5 divided by 60. Okay, so first calculate the risk ratio. All right, so now over here, oh, sorry, I accidentally switched the slide over here. Yeah, okay. So yes, the first thing which you do is calculate your risk ratio, and this is what you have, your risk ratio. It is the same as the earlier calculation. Okay, so what did you end up with? Saturday being 27%, Sunday being 8%. Is this what we had when we calculated risk ratios? Let us see. Saturday being 27%, Sunday being 8%. Okay, so the first thing which you did to calculate attributable risk is to calculate risk ratio. All right, so yes, you have calculated that. All right, so now you have that. Now the simple thing which you do is you do one more step and you minus them. Okay, so you minus Saturday from Sunday. All right, and what do you have? You have 19%. So basically, as I said, in essence, in practical life, the only difference is how you report the results if you have calculated attributable risk versus risk ratios. All right. So now, because you are minusing them, you are comparing the groups by identifying the difference. How would you write something like this? This is how you would write it. 19% of disease risk. And what is the disease over here? It is not disease, but yeah, food poisoning. Okay. So 19% of disease risk, or a health outcome, I should say, food poisoning could be attributed to people attending church on Saturday in comparison to Sunday. Okay, so because you are, as I said, you have minus them, so you are comparing one group against the other group in terms of the differences. Okay, so 19% of the disease risk could be attributed to people attending the church, or food poisoning could be attributed to people attending the church on Saturday in comparison to Sunday. Therefore, again, another way of saying it, therefore, 19% of the health outcome, which is food poisoning, could be prevented if people had not attended church on Saturday, which is quite unrealistic, right? What if I had time only on Saturday? Okay, but this is just as an hypothetical example to show you that the only difference is over here, the way you frame your result. All right, and that makes a very big impact, guys, depending upon what type of research you are doing. All right, so if your research is predominantly looking at a disease group versus a healthy group, you may want to do this one more step And you may want to find the differences between the two groups, and that's how you want to have your comparative statement as. Okay, so you may do attributable risk in that instance. But with a lot of prospective cohort studies, what we have seen is people just reporting the risk ratios. Okay. All right, guys. So yeah. So again, over here, just quickly summarizing, both of these indicators are quite similar in nature. Why? Because they are comparing two groups, one which has the health outcome versus one which does not have the health outcome. Risk ratio is relatively easier, all right, where you're just comparing two groups with the health outcome versus not the health outcomes. And generally, how you report the results is in times, all right. 3.4 times higher, food poisoning is 3.4 times higher among people who attended church on Saturday in comparison to Sunday. Why am I saying this is the lingo which is used with risk ratio? Because if you look at this paper, guys, all right, for instance, the risk of CVD incidence event, all right, the risk ratio is 1.34, goes higher in the lowest category of vitamin D versus the highest category of vitamin D. What does this mean? It means that the risk of having cardiovascular diseases was 1.34 times higher if people were deficient in vitamin D versus if people were sufficient in vitamin D. Like in very simple terms, I'm putting it. Okay. So you see how when I have done my research, I have put it in the right language, use the right lingo when expressing risk ratios. Okay. So it all boils down to how you want to report your results, and is that aligning your research questions. So your supervisor will tell you that, yes, we will be calculating risk ratios and that's about it. But maybe if you have a very unique research question where you truly want to see the differences between your, say, exposed versus unexposed group, then you may take a step further and you may calculate the attributable risk. Okay, so yeah, so what was attributable risk? Again, you're comparing an exposed group versus an unexposed group. How are you comparing them? First step which you do is the same, which is calculate the risk ratio. Then you take one step forward and then you compare these groups by identifying the differences. What is the difference between the two groups? And because now you have calculated differences, there is a way and a style of reporting this result, and this is how it is reported. And this style of reporting result is what I also have explained when I gave you the example of lung cancer, that smoking is attributed to 85% of lung cancer within study 1. All right, so that's the lingo or the language which you use when you are reporting attributable risk. Attributable risk is also called as rate difference, risk difference, so on and so forth. Okay. But yeah, I hope this concept is clear, and both of these calculations are very, straightforward, and basically it's as simple as it can get. All right. Okay, so now moving on to odds ratios. Again, the winner over here is odds ratio, because I would say 99.999% of the studies have and will always report odds ratios. Okay. Your attributable fractions, guys, over here, which I said, if you see this, attributable fractions, all right, attributable fractions are, you can say that theoretically to or conceptually, they are similar to attributable risk. Okay, so basically, what does it mean? It means that it is the unfamous counterpart of odd ratio, all right, and attributable risk is also an unfamous counterpart of risk ratio. All right, so both of these are unfamous counterpart. The essence of and over here the formula again has say differences. It's a bit more trickier, the formula for attributable fractions, as compared to just calculating basically the odds ratios. All right. So again over here it is doing the same thing, which is you're trying to say you are trying to label this association between your IV and your DV, okay, in your case cohort study or your cross-sectional study, in which you cannot calculate the true incidence. All right, why you cannot calculate the true incidence? Because cross-sectional studies are snapshot. You're not following them for 10 years. You don't know when they developed the disease. It's not during the time you were doing your research with them. With case control studies, you already have a disease population and a healthy population, and you're following them. Again, no true incidence being able to calculate. That's why you are calculating odds ratios. Okay. So yes, again, the theoretical foundation is the same. When would you calculate, say, attributable fractions? To be honest, till date, I haven't seen any research paper that I have come across in my area of practice. And my area of practice is nutrition and dietetics. Okay. So in my area of practice, I haven't come across one research paper where I have seen a researcher calculate attributable fractions using odds ratio. Okay. So this is quite rare in my area of research. Probably it could be, say, a bit more, visual, or maybe a bit more, it may have a presence in some other, say, health faculty, but not very popularly used in mine. Okay. All right, guys. So now with odds ratio, so yes, again, remember odds ratio. What are the key points to remember? Calculated for cross-sectional studies, case control studies. And when do you calculate them? When you don't have your true incidence, when you cannot identify the true incidence. Okay, that is when you calculate odds ratio. Essentially, it is, what is it trying to do? It is trying to do something very, very similar to risk ratio, which is trying to identify or label a relationship between your IV and your DV. And when you're labeling a relationship between your IV and your DV in a cross-section or a cohort case control study, this relationship or this association is termed as odds ratio. Okay, and it has the same sort of concept. Odds ratio greater to 1. What does it indicate? Increase, say, occurrence of the event. Less than 1, decrease occurrence of the event. Okay, and then you have a formula for this. So let's again look at an example. So yes, cancer, no cancer. So again, yes cancer, no cancer, meaning you have a group which has cancer, the other group does not have cancer. So yes, true incidence is not possible to be identified. And then you are seeing how many of them smoke and how many of them do not smoke. All right. So now in this example, how do you calculate odds ratio? Very, very simple. It's just cross multiplication. I have written over here A, B, C, D, so it's easier for you to see. So you have A into D, which is A into D over here, and you have your B into C. Okay, so you do that and you get a odds ratio of 4. So what does this 4 mean? How would you put it in terms again? So as I said, when you do all these sort of calculations, risk ratios, attributable risk, odds ratio, it's just how do you write them? Okay, so you would say over here, individuals smoking are 4 times more likely to develop cancer than individuals who do not smoke. As simple as that. Guys, papers, there are research papers who also report that, who also report it in this manner, which is individuals who smoke are 4 times more at odds of, say, developing cancer than individuals who do not smoke. So they may use the term odds in writing the result statement. Okay, so just letting you know, this is how you would use. One thing which you will not do is to use the term risk. Okay, do not use the term risk if you have calculated odds ratio. When you're writing your results, as I said, this is all doing the same thing, which is trying to make comparisons between your IV and your DV in various type of study designs. Okay, so the theoretical concept is the same, the essence is the same, but it all boils down to how you want to report your results. So if we see over here, you see how we have used the term risk when we are calculating risk ratio, all right? The risk of food poisoning was 3.4 times. Okay, so I have used the term risk. Do not use the term risk when you are calculating odds ratio. Okay, so you see how I have written the result over here. Individuals smoking are 4 times more likely to develop cancer. Okay, I have used the term likely, not at risk of developing cancer. No, likely to develop cancer than individuals who do not smoke. Okay, so that has a more, say, statistical connotation, where when you calculate risk, you are free to use the term risk. But when you calculate odds ratio, use terms like are at odds of developing or likely to develop. These are the type of terms you use. Okay, why? Because if you go to publish your, and if you have calculated odds ratio and you keep using the term risk, your reviewer will say but you are not but your study design does not give you the opportunity to calculate the true incidence. Okay, you do not have the true incidence. Then why do you keep saying risk? Okay, so risk generally is more applied when when you have the opportunity to see the true incidence in your population when you're following them for 10 years. Okay, but you don't have that opportunity in case control studies, cross-sectional studies. That is why you have say researchers refrain from using the term risk when say having results for odds ratio. Okay, so I hope this makes sense, guys, the practical connotations of all of this. Okay, so that's again the maths behind calculating odds ratio. So yeah, attributable fractions, as I said, again, it's the unpopular brother. Never seen it in my area of research. Maybe you may come across, you know, if you're lucky, a paper which has calculated attributable fractions. That's so random. These slides just suddenly changed. Okay. I'm recording at night, so no, there are no ghosts around. Okay, there is nothing like ghosts. Anyways, okay, yeah, it's quite tiring. I'm a bit tired, so sometimes I just make silly jokes and I'm the only one laughing because it's pre-recorded. Okay, so yeah, attributable fractions, guys, again, are not very popular. Odds ratio is what is reported by 99.9% of the papers. Okay, and what's the formula for it? The formula for attributable fractions is odds ratio minus 1 divided by odds ratio into 100. Okay, you have an entire mathematical derivation as to how did they come about this formula. It is not as simple as and as beautiful as your attributable risk. Okay, where did our attributable risk go? Yes, where you just have a difference, and the main theoretical connotation over here is you're trying to find the difference between these two groups. You have an entire mathematical derivation from as to how you came about this formula. And I don't think so it is there in the textbook over here, which we generally use for this, this unit, which is your web one. But yes, there are very advanced epidemiological books and mostly books related to biostatistics. Okay, biostatisticians are more interested in how did this formula be derived from it. So what is the mathematical context behind it? So yes, of course, I'm not going to go into that. But if you are interested, look up biostatistics textbooks to identify and to understand how did they come about, what is the rationale for coming about this formula to calculate attributable fractions with odds ratio. Okay, so in case if you're interested. But yes, for me, how do I apply this formula in an example is what I'm interested in. So yes, let's look at this example again, same example, so we can see the comparison. All right, so yes, it's the same example. You have individuals with cancer, without cancer, and then you want to see if they were smoking and if they were not smoking. Okay, so as you see in the formula, the first thing which you need is odds ratio. Okay, if you see, the theory is so similar. Even to calculate your attributable risk, where is it? Yes, to calculate your attributable risk, the first thing which you need is your risk ratio. When you have your risk ratio, then you can get the difference, right? So the same sort of theory applies for attributable fractions, which is to use this formula, you need odds ratio. Okay, so we know in this same example over here that our odds ratio is 4. Okay, that's why it's green in color. See, all of these coloring, it helps me to register. So yes, 4 over here is green in color. And it's the same example. So the odds ratio were 4. And then when I come to this formula, I have this green color 4 over here again. Again, it helps me to map the slides in my head. All right. So yeah. So now you have odds ratio of 4, which we know, which is for this example. I input this odds ratio over here, which is 4. And then everything is the same, which is minus 1 divided by 4, which is your odds ratio into 100. What do you have? 75. Again, now it is the style of writing and reporting your results. Okay, so if you have calculated attributable fractions, how would you report your results as? In writing, this is how you would report your results, that 75% of cancer among subjects smoking could be attributed to the fact that they were smoking. Therefore, 75% of cancer could be preventable if these sample subjects were not smoking. So you see, the style of writing is so very much similar to our attributable risk. So if we look over here, you know how we have kept using the word attributed, and we have two ways of writing it. One is that 19% of attributable risk. I use the word risk over here because it is attributable risk. All right. So 19% of disease risk can be attributed to people going to say the church on Saturday compared to Sunday. And then the second way of writing it is 19% of this disease risk or food poisoning could have been prevented if people did not go to the church on Saturday. Okay. Similarly is how you would write a result for your attributable fraction. But you see over here, again, you cannot use the word risk. Okay. So that's why it's like, again, similar concept, but I cannot use the word risk. So what sort of wording would I use? 75% of cancer among subjects smoking could be attributed. And I haven't said risk, but I have said to the fact that they were smoking. And then again, the second way of writing it, therefore, 75% of cancers could be preventable if the subject sample were not smoking. Okay, so I hope this makes sense, guys. These are very simple concepts. And it's just as I say that the style of writing the results is a bit different depending upon what you calculate. And the most common thing, again, to summarize what you see in papers, is your risk ratios versus your odds ratio. Risk ratio, you are free to use the term risk. Odds ratio, use terms such as likely or are at the odds of, use things like that. Okay. So yeah, that's where I sum up the calculation bit of this, say, this lecture, as simple as it can get, really simple calculations. Now we go on to really important concepts, which is reliability and validity. Very important concepts, guys. Again, theoretical in nature, but what I'll try to do is show you examples from my research where you can see that how this is applied in practice. Okay. All right. So what does reliability mean? Reliability means, say, repeatability and consistency. Meaning, for example, that if I say measure myself on a weighing scale. Okay. So generally, say families, we would be having a weighing scale at home, right? So if I measure myself on a weighing scale, it should give me consistent results. Meaning, one time I can't be, say, 52 kgs, and the other time I'm 62, and then the third time I'm 75. What's going on? Okay, that's not consistent. What is consistent? 52 kgs, maybe 52.0, then maybe again 52 kgs. That's consistent. All right. So that is reliability. Okay, so that weighing scale is reliable because it is giving you consistent results. All right. No matter how many times you are doing it, it is giving you consistent results. Okay, so that is reliability. Now with validity, what does it mean? It means truth and accuracy. It means a weighing scale should be able to measure weight, all right, not show you height. Okay, so for instance, when you stand on a weighing scale, and if it is supposed to measure your weight in kgs, all right, it should give you 52 kgs. That can't give you pounds. Okay, if it gives you something like, say, 150 pounds or something, and then you'll freak out. You'll be like, oh my God, am I 150 kgs? No, I'm not. Okay. So validity means your instrument or your tool should accurately measure, and it should measure what it is supposed to measure. A weighing scale cannot measure height or should not measure height, and a say a stadiometer is what you use to measure height, that cannot measure weight. Okay, so validity is the truth and accuracy of what is what the tool which you have. Okay, so yes, reliability and good validity are very, very important to produce systematic, which is or the other term which we can use is consistent. All right, so systematic is your say consistent and accurate finding. Accurate is an indicator of your validity. Systematic is an indicator of reliability, meaning consistency. Okay, so that's why it's very, very important to have a decent reliability and validity when you're doing your research. Okay. Okay, so reliability, as I said, it is the consistency in the measurement, All right, so there are various types of reliability. The most common types is what I have say covered for you. All right. Similarly, guys, for the measures of association, the most common ones is what I have covered for you. If you're interested in this topic further, which is above and beyond the scope of this, this unit, but you are very free to keep reading on it, is go to this textbook and you can read up other measures of associations which are out there. But of course, you will be only assessed on what I teach you, okay, which is these 4 measures of association that we have covered. But you are very free to read upon, say, more measures of association. Similarly, there are many types of reliability and validity indices. The most common ones which we observe in health research is what I have covered as part of this curriculum. But you're free to read up on many others in those additional readings that I have provided. Okay, so none of those additional readings are like something which I'll open and I'll say develop a question from. That's not fair, and I won't be doing that. Okay, so yeah, so now you have the first type of, say, reliability is your test-retest reliability. So what is test-retest reliability? This is how I did it in my research. So let me share with you. So this is my research, okay? So what is the tool which I developed? The tool which I developed is a questionnaire which was completed by the mothers. And what did I try to find from the mothers is whether mothers perceive their children to be picky towards certain fruits, vegetables, and food items or not. Okay, so that was basically what I wanted to study, mothers' perception of their children's picky eating behavior. Okay, what is test-retest reliability? I asked the mothers to complete my questionnaire. All right, then within a span of 4 weeks, I asked them to complete the same questionnaire again. And then I compare the responses on both of these questionnaires. And my intention is to see, are these mothers giving me accurate findings? If, for instance, if they have said for the first time that their child is very picky for broccoli, their child hates broccoli, within a span of 4 weeks, I shouldn't be having a response where the same mother is saying, my child loves broccoli. Okay. Why? Because in my research, food preferences do not change overnight, okay, in children. Yes, if you're comparing food preferences when you were a child and when you were an adult, that's a different story. But food preferences within a span of just 4 weeks in children do not dramatically change. That is what the theory is telling me. That is what my literature is telling me. And you do test-retest reliability. How do you do it? Why do you do it? How do you do it is you ask your participants to complete your questionnaire or your tool again. All right. So that's how you do it. Similarly, if it was not a questionnaire, you may weigh your participants 3 times. Okay. That's what something else which we do in nutritional epidemiology is. We weigh the participants 3 times and there may be slight differences or maybe no differences in the reading. 52 kg, 52 kg, 52.1 kg. Okay, and then you take an average of it. This is again test-retest reliability. All right, where what do you mean by that? It means the same instrument when it is administered more than once, and you are comparing the findings between those readings. Okay, this is for FYI for those who are interested for a bit more advanced epidemiological content. The way you compare your say readings or your findings between your first administration and your second administration is using intra-class correlation coefficients, ICC, intra-class correlation coefficients. Why am I telling you this? Is because a lot of papers will report this term ICC, intra-class correlation coefficient. It should make sense to you. You should be able to identify and say that, oh yes, I know what ICC is. Basically, they are doing test-retest reliability, meaning they have the same tool and they have administered it twice or maybe thrice over a period of time. And then they are comparing the readings between all of this, readings for the same tool between different time points. Okay. So essentially, that is your test-retest reliability. Okay. So now what's the second one? Second one is inter-rater reliability. Inter-rater reliability is generally done when, for example, when I have an experimental setting, I have invited children in a food laboratory and I have placed certain, say, foods on a table. And I have, as an observer, I'm seeing what is the child picking, what is the child eating, what is the child not eating. And then I have another colleague of mine, a researcher, she's doing her own observations. And then we compare notes. This is called inter-rater reliability, meaning 2 or more trained researchers are recording the observations from the subject, and then you're comparing your notes to see that you do not have any researcher bias. Okay, it's not that because I want my research to succeed, I have my own bias in interpretation, where I say that, oh, all of the children in the food lab, they hated broccoli. And whereas she may say that, yes, 7 of the 10 children did not like broccoli, but 3 of them loved it and they ate all of the broccoli on the plate. All right, so it shouldn't, to minimize these discrepancies, you may have 2 trained researcher colleagues who are doing the observations on the sample population. This is inter-rater reliability. What is internal consistency? Internal consistency is, let me explain to you again in a real life example. Okay, so if you look at this, let's look at this. All right, so internal consistency says that when you are clubbing up a bunch of items and you are calling this a construct, okay, then these items should be items which logically should be clubbed together and they make sense. Okay, so for instance, this construct of mine, this is called construct, or this is also called as a factor. All right, and in quite advanced level papers, this is also called as a latent variable. All right, so this construct of mine is basically measuring children's food preferences towards savory discretionary food items. What are discretionary food? Junk food, all right, and soft drink. All right, so this construct is basically, I want to see if children are liking specific savory tasting junk foods or not. Savory meaning they're not sweet. Okay, so I can't have basically anything over here which is sweet. All right, so your chips and your fries and your burgers and your noodles, all of this is not sweet in taste. Okay, this is not like chocolate, candy, ice cream, stuff like that. And then you have your soft drink. So these items are clubbing together. They are making sense to be clubbed together and to be formed one construct. All right. Then I have another construct which is trying to measure children's preferences for junk food which are sweet in taste. Okay. So your sweet in taste are things like your biscuits and your ice cream custard puddings and your chocolate candy lollies. Okay, and your Cocoa Pops and your Fruit Loops and stuff like that. So all of this is sweet. So the sweet thing is forming one construct. Savory things are forming one construct. Okay. And basically, how do I know statistically that these items are sticking well together? It is all right to club them together. They are meaningful together. Again, for that, I calculate something like internal consistency Cronbach alpha. Okay. So statistically, for so all of this tests are done in SPSS. These are really simple tests. So Cronbach alpha can be calculated in SPSS, and that will tell you whether you have good internal consistency or you have poor internal consistency. So what is good internal consistency? Good internal consistency is when you have a Cronbach alpha of say 0.9, 0.8, 0.7. Generally in the literature, it says that if your Cronbach alpha is equal to or above 0.7, you have a pretty decent construct, meaning these items are going well together and they should be clubbed together. Okay, so let's look at this, say Cronbach alpha. Let's look at the same example over here. So you know how I had an example of savory junk food and then you had the sweet junk food. So savory junk food had a Cronbach alpha of 0.8, really good. Okay, sweet junk food had a Cronbach alpha of 0.7. And I have almost met the mark, so I'm safe. Meaning I have really good internal consistency. These items being clubbed together are making sense. It's okay to club them together and then to call them as one group of items. Okay. So that is what it means by internal consistency. All right. So these are the most common one which you will see in health research across your disciplines. All right. Then you have validity. So what is validity? As I said, your instrument should measure what it is actually supposed to measure. All right. And so over here, what are the various types of validity? Again, I'll be touching base on the most common ones which you will see in the literature. So content validity. So what is content validity? It means that how well your tool or questionnaire measures what it is supposed to measure. So what does this mean? It means that, and who will be be a judge of this, that your questionnaire is measuring what it is supposed to measure. So now for content validity, generally you do not have a sophisticated statistical test like the ones which I showed you for content validity. But basically how I have tested content validity is, I developed my questionnaire, this picky eating questionnaire, where moms were telling me whether their children are picky for certain foods, vegetables, and whatnot. And then I asked 3 dietitian experts. They are very, very prominent and very, very experts in their field. I asked them independently to review my questionnaire, which I had developed, and to see whether the items in the questionnaire make sense. Okay. So for instance, if I have, say, food items such as broccoli, cabbage, apple, mango, stuff like that, and then suddenly if I have, say, a ball pen, does that even make sense? Like, why is a stationary item suddenly coming into a questionnaire which is supposed to measure, say, child's perception of a mother's perception of child's pickiness? Okay, so this is what I'm saying. So content validity is where your questionnaire should measure what it is supposed to measure. Who will be the judge to decide that? The way I have done it in my paper is by inviting 3 experts, and they are independently reviewing my questionnaire, and then they are providing me feedback. Okay. So for instance, yes, this is a good one. Rather than ball pen, that was a really sad example. But yes, one of the items which I had in my questionnaire, it was called as brinjal. All right. We don't use brinjal in Australia. Okay. That's a very Asian term. All right. What you use in Australia is eggplant. So one of the reviewers said, don't use brinjal. Your moms will be like, what is this questionnaire measuring? What is brinjal? What you should be using is eggplant. Okay. So stuff like that. All right. So that's your content validity. What is face validity? It is the same thing. It means your questionnaire should measure what it is supposed to measure, and it should be able to be well understood by your participants. Okay. So yes, this is very important. So again, with face validity, no formal statistics out there to calculate your face validity. But basically how I have, say, confirmed face validity for my questionnaire is, I did a pilot study. I invited 15 mothers to the university. They completed the questionnaire. Then I had one-to-one interviews with these mothers to see whether they understood the questionnaire, were there any things which they did not understand, were there any misinterpretation, and stuff like that. So via a very qualitative approach, a dialogue, a discussion, I gathered their feedback, and this is how I confirmed face validity. So you see how for certain things you don't have these calculations, you have more of a qualitative approach. And a few examples are for content and face validity. Okay, then moving on further, construct validity. Construct validity is as quantitative as it can get, as statistical as it can get. All right, and I'll show you how. So again, construct validity, there are 2 types. You have convergent validity and then you have divergent validity. Convergent validity means, it means that when you have these items which are representing a construct, are these items representing a construct well? All right, so it is quite similar, guys. It is quite similar to your, where did we go? Yeah, it's quite similar to your internal consistency. Okay, but convergent validity is much more robust. What do I mean by it is robust? It means it has such advanced statistics behind it that if you do that statistics and if you have good convergent validity, meaning your construct is fantastic. Okay, so let me show you an example again from my research paper. So over here, if you see, convergent validity is trying to do the same thing. Convergent validity here, this one, it is trying to do the same thing as your internal consistency, which is Then you have these bunch of items, all of these items. Do these items make sense when they are clubbed together into one group or one construct? Okay, that's the same sort of thing that it is trying to express. Okay, but convergent validity, the type of statistics that you do to calculate convergent validity, is highly sophisticated. Okay, so what do you calculate for convergent validity? You have two types of indicators which you calculate convergent validity with, is average variance extracted, AVG. Again, this one is advanced level knowledge only for those who are interested. So convergent validity is calculated by certain statistical methods. These are advanced statistical methods. The maths behind that is much more sophisticated than your Cronbach alpha. Okay, so your AVG, average variance extracted. Okay, and then you have a second thing by which you calculate convergent validity. It is called as composite reliability. All right. So now I'll show you a good example over here how, like, means I am in a little bit of trouble, but then I have other things to justify. So that's research. But if you see over here, average variance extracted and composite reliability is what you calculate to express convergent validity. Now your AVG above 0.5 is considered good. Like how you had Cronbach alpha above 0.7 was good. All right. So AVE above 0.5 is good. Then you have your composite reliability. Composite reliability above 0.7 is good. So composite reliability is very, very similar to Cronbach alpha. Both of them above 0.7, meaning you have good composite reliability. Over here, you have good Cronbach alpha, internal consistency. Okay. Now, if you see, how I told you that convergent, the maths behind convergent validity is much more sophisticated. Let me show this to you over here. So if you see, how, why did I say maths is more sophisticated? Is because if you remember, how for my sweet junk food construct, all right, I had Cronbach alpha of 0.7, and how I did few, I just met it. Okay, and I was very happy that I just met the cutoff of what is considered good in the literature. All right, so I have just met the cutoff over here. I have just passed. But if you see over here, my AVE, average variance extracted, is 0.4. Okay, meaning it is less than 0.5. Okay, what did I tell you? Anything which is 0.5 and above is good. Okay, AVE of 0.5 and above is considered good. I am above the minimum expectation of what is considered good over here. And if you see, the composite reliability over here is 0.7, so that is fine. Okay. So in this cases, when you have one indices which is not met the cutoff, what do? That is advanced level research. I won't go into that because that will become a biostatistics course. You don't need to know about all of that at this stage. If you're interested, of course, we can have a chat about it in our interactions. That's different. Okay, so yeah. Here, all you need to know is convergent validity, like internal consistency, is trying to do the same thing, which is trying to see whether the items which you have in your questionnaire, are they holding well together as a construct? Okay, that is what it is trying to see. All right. Other thing which will help you to understand the concept in real life is the statistics and the maths behind convergent validity is much more sophisticated in comparison to internal consistency. That is why researchers like me report both of these things. Okay. So yeah, that's your construct validity. What is divergent validity? Divergent validity is to show that when you have all these different constructs, to show that these constructs are different. They shouldn't be clubbed together. Okay. So let me share with you an example of this again. So yes, look at this. So now guys, I have under the canopy of dairy. Okay, dairy is your milk, yogurt, and all of that. Okay, so cheese and stuff like that. Under the canopy of dairy, I have two constructs and I have proposed them to be different in nature. Okay. When I have made a hypothesis that my two constructs are different in nature, This means that I need to prove that they have divergent validity. So what is divergent validity? In a canopy, you have these constructs and you are proving that one construct is different from another construct. I should not club these constructs together and make it into one construct. No, I need to keep them as two separate constructs. Okay. So yeah, so over here I have a dairy construct over here, which is called as picky dairy. Picky dairy meaning mums are saying that their children are picky for these dairy items. And not picky dairy is where mums are saying that their children love these items. Okay. So which dairy items are children picky towards? It's plain milk and plant-based dairy, like your almond milk, soy milk, and stuff like that. Then you have your non-picky dairy items, which meaning the children love these items. This is your cheese and plain yogurt. Okay. So when I did all of the stats behind this, okay, so I do this sort of diagram stuff. This diagram stuff is called as confirmatory factor analysis. It's the gold standard for testing construct validity. So again, this is an advanced level information. So the gold standard for testing construct validity using statistics is called as confirmatory factor analysis, CFA. Okay. So when you run CFA in one of these softwares, which is AMOS. AMOS is something which is available in University of Canberra. That's why I have used it. So you cannot do confirmatory factor analysis in SPSS. Okay. You have a brother of SPSS because it's by IBM people as well. It's called AMOS, in which you can run confirmatory factor analysis. AMOS gives you these lovely diagrams. Okay. Don't worry about all of these sort of numbers. This is all really advanced biostats, which you don't need to know. You just need to know the essence of it. So basically, what am I saying? That with divergent validity, when I run this sort of, say, diagram, do statistics on this diagram in AMOS, which is the software, it gives me certain numbers. All right. This certain numbers helps me to confirm that I have good divergent validity. So with divergent validity, you do not have a black and white cutoff like more than 0.7, less than 0.7. No. With divergent validity, you actually have to run the sophisticated analysis in a software, in a sophisticated software, and then you have an entire equation which comes out, and that equation will tell you whether you have good divergent validity or not. Okay. So I hope this makes sense, guys. So what does divergent validity mean? It means that when you have these different constructs, you want to prove that this construct A is different from construct B. Do not combine them and make them into one construct. They are essentially measuring different things. Like in my construct, one was measuring love for dairy, the other was measuring hate for dairy. Okay. So yeah, I hope this makes sense. Then you have relative validity. Relative validity is where you compare your tool to a reference benchmark, okay, for something which is already published, validated, acknowledged, and respected in the literature. Okay, so what does this mean? It means that, let me show this to you how I did this. Oh, so much of talking, I need to catch a breath. Okay, so relative validity. So with relative validity, how I did it was, for instance, I had something which is, I have my questionnaire, and you know what my questionnaire is doing. My questionnaire is asking the mothers whether their children are picky or whether they love certain food and food items. Okay. So I have my questionnaire. Then I have this one more questionnaire out there in the literature, which is called as the food preference questionnaire by Dr. Anna Flight. Okay. Now, Dr. Anna Flight's questionnaire is somewhat similar to mine. Okay. She also has a bunch of food items, and she is asking British mothers to tell her that whether her children are picky or not picky, or whether they like or dislike certain say food items. All right. So what relative validity is, you compare your questionnaire to a existing validated or well reputed questionnaire in the literature. Okay. How do you compare them? is statistics again. Okay, that's why epidemiology, you can't separate statistics from epidemiology. Epidemiology teaches you the theoretical concepts. Statistics is application and practice. All right. So in relative validity, how do you do relative validity? Relative validity, the stats with how you compare your questionnaire to a reference benchmark, the stats you do is called as Balt-Allman. Okay, so I may be pronouncing it terribly, but this is how it's written: B-L-A-N-D and A-L-T-M-A-N. Okay, so this is how it's written. Okay, so this is what it's say a big researcher's name, and he named the stats after himself because he had invented it. Okay, so this is again just an FYI. Why? Because whenever we say, so how do we measure these reliability and validity? Well, this is how you really measure this reliability and validity. It only makes sense when you know that how is it measured in real life. Okay, if I just give you these black and white theoretical definitions, it just won't make sense. I mean, like, yeah, so you measure your questionnaire, you compare it against a reference questionnaire. But how do you do this? You do this via stats. What is the stats you use? You use Balt-Allman stats. Okay. So yeah, that's how you do your relative validity. Okay, by a Balt-Allman test, where you're comparing your questionnaire against a reference benchmark and seeing if mothers on your questionnaire are saying that their children hate broccoli, and the reference questionnaire also is measuring likability to broccoli, and if mothers on that questionnaire are also saying that yes, my children hate broccoli, meaning your questionnaire is amazing, it's not misleading, mothers are correctly being able to interpret your questionnaire, because on your questionnaire and the reference questionnaire, mother has said the same thing, meaning her child hates broccoli. Okay, so that's your relative validity. What is internal validity? Internal validity is basically a concept in which you have the confidence of saying that your independent variable is the only one which has caused the outcome or the dependent variable. Okay, and internal validity is generally done more when you have say, for instance, okay, so let me tell you this. So this questionnaire which I have, for example, this one, all of this, where I have asked mothers to complete this questionnaire. My study was examining Indian mothers living in Australia, their perception about their child's pickiness. Okay, so that is internal validity, meaning I cannot, I have developed this questionnaire for Indian mothers who are living in Australia. And this questionnaire is working for Indian mothers living in Australia because I have really good reliability, validity, stuff like that, as we have seen. Okay, I'm meeting the cutoffs and the markers. All right. So yes. So with internal validity, my population of interest is Indian mothers in Australia. This questionnaire has been completed by 482 Indian mothers in Australia. Okay, meaning I cannot now say that, oh, but other mothers in Australia can also use my questionnaire, meaning Caucasian Australian mothers, or Italian Australian mothers, or Chinese Australian mothers, or maybe a mother sitting in the UK. That is wrong. All right, internal validity in this context, in my questionnaire context, means that my findings are only applicable to the Indian scenario in Australia. Okay, Indian mothers in Australia. That's about it. I cannot make big generalizations. All right. Now, do understand, internal validity concept is also widely used when you are doing studies such as randomized control trials. Okay, in randomized control trials, for example, if I want to see, for instance, that say iron supplementation, the iron supplement which I have created, a natural organic iron supplement which I have created, that helps to decrease anemia among pregnant women. Okay, so this is where internal validity concept comes into the place again. Meaning I want to be confident in saying that mom's anemia has decreased because of my organic iron supplementation. All right, not because of other factors. What if the other factors were like, say, for instance, to increase her iron, where like she had actually taken, say ferrous, say ingestions and things like that. She had taken intravenous, say iron for a couple of say time, or maybe menstruation has stopped and therefore her blood levels have increased, or any other thing. Maybe she has started eating a lot more iron-rich foods in her diet. That's why her iron is increased. All of these are other variables which may influence the outcome. What is the outcome? Reducing anemia, okay, which is iron deficiency. All right. So internal validity as a concept is applicable for various sort of study design. All right. You have good internal validity when you have the confidence in saying that the outcome has happened, meaning decrease in anemia, decrease in iron deficiency. The outcome has happened because of my independent variable. What is my independent variable? Organic iron supplement. Okay, does that make sense? All right. And how can you be confident? How can you have good internal validity? When you control for confounders. What are confounders? You will learn more about that in your coming chapters and lectures. Okay. So right now, to understand, internal validity is a concept. How this concept is applied depends upon the various type of study designs and the research questions which you have. Okay. For my research, that questionnaire development, this is how internal validity was constructed. It was only for Indian mothers in Australia. If I was doing a randomized control trial, internal validity as a concept would have a different meaning. Why? Because I have an IV and a DV when I'm doing a randomized control trial. Okay. What is external validity? It means having the power for generalization. Power for generalization, meaning where you can say that people beyond your study would be having the same sort of effect. Okay. Meaning you have done your iron supplementation study on, Australian Caucasian, say women, and you have seen amazing results. And maybe your randomized control trial was done at Canberra Hospital. And because you have done a very good randomized control trial, controlled for confounders, you have done all of the stats right. That's why you may make a claim in saying that this sort of results could also be applicable for the wider Caucasian Australian population. All right. So yes, there are instances in which you can make these strong claims. All right. And but for that, you need to have a very, very rigorous study design. All right. Okay, so that's your external validity. So now threats to internal and external validity, meaning what are the things which may weaken your internal and external validity, and you can't like say address all of these say threats, but good research demands you to acknowledge these threats. Okay, so there is a difference. There are certain threats which you can control, you can modify, you can reduce, you can address. But then there are other threats which you can't really do anything about, and you just have to acknowledge them. Okay, so now let's look at these threats. So the first one is what is a threat to internal and external validity? Is ambiguity for the direction of the relationship between the independent and the dependent variable. Okay, meaning when you have an independent and dependent variable, and when your variables are such that you cannot really say establish a cause and effect relationship, then this is a threat to your internal and external validity. Okay, and as I said, not everything can be controlled. Some things have to be acknowledged. And let me give an example of that. So for instance, my PhD thesis long back was looking at children's picky eating behavior and their moms pressurizing them to eat fruits and vegetables. Okay, so now literature has shown that there is a bi-directional relationship between children's picky eating behavior and mom's pressure feeding practices. What is pressure feeding? When you're really like pushing food in your child's mouth and you really want them to finish their peas and broccoli and whatever they have on their plate. Okay, so basically the literature said that actually because the mothers are pressure feeding, that is why the child is like showing all this picky eating behavior, like throwing tantrums and crying and saying, I don't want to eat, stuff like that. So that's picky eating behavior. Okay. Or else it could be, but the moms were arguing, no, it's the other way around. It is because my child is acting all fussy and does not want to eat. That's why, unfortunately, I have to pressure. So you see how the IV and DV have a bidirectional relationship. So in this condition, basically, I, as a researcher, when I studied this topic, I had to acknowledge this in my limitation section, that I have a bidirectional relationship between my IV and DV, and true unidirectional relationship cannot be established. Okay. So yes, I am acknowledging that this is a threat to validity of my findings, and I acknowledge it because there are certain human behaviors which are not unidirectional, and that is the beauty or maybe the challenge of doing human research. Okay, not everything is unidirectional. All right. Okay, then I said confounding variables. You will learn a lot more about confounding variables in your coming lectures. But basically, what is confounding variables? Something which I covered briefly. The example which we had was, for example, I have this amazing organic iron supplements, and I claim that it will decrease iron deficiency anemia among women. But there could be many, many other variables which may have decreased the mom's iron deficiency anemia. This could be that maybe the mom is having an iron-rich diet now, or maybe her menstruation has stopped, and that's why her iron levels are increasing now. So yeah, stuff like that. Okay, so there are many, many things which could have led to a better iron status in the woman, and it may not just be my organic iron supplement. All right. So what do I do about all these other tricky variables? There are various ways to address these confounding variables. I won't go into details of this because you will be learning about this in your coming lectures. But just understand, when you have confounding variables, they are a threat to your internal and external validity. But there are strategies to control and manage these confounding variables and to improve your internal and external validity. Okay, and this is what you will be learning in coming chapters. Okay, instrumentation. This is really simple, guys. And so let me tell you an example to explain this again. So I had these students who were, say, under my supervision, and they were going out in the field for data collection. And we had these well-calibrated weighing scale, and they had to take this weighing scale, which was well-calibrated. How do you calibrate weighing scale? That's like another, means discussion. But basically, a calibrated weighing scale is like a very, very accurate weighing scale, which should have amazing, say, validity. Okay. So we had this amazing weighing scale. We had calibrated it, and the students were supposed to take this weighing scale only for all of their measurements to measure the weight of their participants. Okay. Once what happened is that the students split up into two groups, because one had to do data collection in North Canberra, the other had to do it in South Canberra. One of the groups took the weighing scale, and the other one just took something which was lying in their house. Okay. This is a threat to internal validity. All right. Why? Because that second instrument is not calibrated. The something which was there lying in somebody else's house, that instrument is not calibrated. You have changed the instrument. So change in calibration, change in instruments, all right, can increase the threat to your internal and external validity. Change in observers. For example, within the students, there were two students who were trained to measure height and weight. Okay. If one of these students is absent, you had the other student to support and would measure the height and weight. But if both of these students are not there who are trained, and then you have others who are just doing some random stuff, then this is also a threat to internal and external validity. Okay. So that is called change in observers. All right. Then you have scorers. Same goes for researchers. For example, you know how I said that in an experimental setting, I am observing what the children are eating and not eating, and my colleague is observing what the children are eating and not eating, and we are the one who are assigned to be taking these notes and recording this and scoring the children for all of the trials. What if for a couple of trials we are absent and somebody else is taking our place? This is not acceptable. Why? Because we have been trained and we have been say advised to follow certain protocol, an untrained person coming in and taking your place, this may create discrepancies in the finding, and this will increase your threats to your internal and external validity. Whenever validity is compromised, whenever reliability is compromised, you are at an increased risk of type 1 error. Okay. All right. So now you have repeated testing. This is quite interesting, guys. In repeated testing, for example, what does this mean? It means that, for instance, if I did a pre-post intervention, okay, I asked moms to complete a set of questions, and then I gave an intervention, and then immediately afterwards, I asked them to complete these questions again. Now, because they have remembered the questions, it may not always be that you have, because you have given such an amazing intervention, they have given really good responses post-intervention. That could be a reason, but you will always have, say, critiques, and you have a lot of devil's advocate in the space of research. They will question the authenticity of your research. How they will say that, oh, it's not because of your intervention that they did really good post-intervention. It's because they remembered the questions, and then maybe they Google up the answer, or now because they just know the questions, they reflected on these questions, and that's why they have answered well. All right. So what are the ways to say, what are other ways around it? So yes, you ask them questions, you give them an intervention, then you ask them questions on those similar topics, but maybe they are not identical questions. Okay. So maybe it could be things like, for example, if it was like with children, if I tell them out of apple, banana, and grapes, which is considered a, which fruit is high in vitamin A, like something random. And if they say apple, okay, then I can't have the same question, in my post intervention. Within that same concept, just have a similar question, but it's different. So yes, it's measuring vitamin A knowledge, but maybe you have 3 different fruit and vegetable options. Does that make sense? Okay. So that's one way around it. The other way around it is that maybe you do a follow-up. Maybe you ask them, say, questions after 3 months and 6 months and 12 months. And if they consistently are giving you, say, accurate responses, meaning your intervention is the one which is actually working. Okay. And these could be sets of, say, similar questions, which is, focused around your intervention. Okay, so yeah, that's repeated testing. So repeated testing could be a threat to internal validity, all right? But there are ways around it, the ones which I shared with you. Okay, so yeah, so now you have diffusion and compensatory rivalry. So what does this mean? It means that when you have cross-contamination between your intervention and control group, and this has happened, unfortunately, in one of my research. So when I was in India, I was doing my postdoctoral studies in India. At that time, we had one group of mother, and this was with Cornell University in United States. Our intervention was to give, say, micronutrient fortified supplementation to mothers in the intervention group, and they would sprinkle this micronutrient fortified supplement on the child's food, and this would then improve the child's iron, zinc level and stuff like that. And the other control group, Cornell said at that time that they won't be having anything. They would just be having guidelines such as increase your say fruits and veggie intake or stuff like that. Okay. Then what happened was that unfortunately, moms in the intervention group were friends with the moms in the control group, and they showed the intervention moms were like, we got this lovely little sachet, and now we are excited to try this with our kids, stuff like that. And the moms in the control group were like, oh, we feel so sad, we didn't get anything, and the stuff like that. And then the moms in the intervention group, they gave half of the sachet to the moms in the control group. This is cross-contamination, all right? This is going to weaken your effect size, this is going to weaken your results, and you cannot prove that your IV is causing your DV, and maybe you can't see any, say, differences between the intervention and control group because everybody is having micronutrient supplementation in some capacity, okay, hidden or formal. So that's not nice. So what is a way around this? The way around this is, this was during a pilot. Good, we picked it up in the pilot because then we designed a cluster randomized control trial, meaning moms in, say, one village or one tribal sector where our intervention group, and mom way beyond in the other village, in the other tribal sector, they were control group. So they just did not know each other, no interaction, very, very far away, physically located. And that's how we did the intervention, and it was a success. Okay. So yeah, this is called as diffusion. You do not want diffusion to happen. Very, very big threats to internal and external validity. The other one is called as compensatory rivalry. This is the same thing which I said, where your control group knows that they are a control group and they are not receiving that special treatment, all right? And that they are receiving, say, a placebo, and sometimes they could be completely discouraged, and they may just not want to participate in your study. They may be dropouts, or else it may go the other way. Because they know they are receiving placebo, they will try 10 times harder to prove that how good they are, and they may do things which is not part of their daily, say, lifestyle or practice to, say, give better results. And this will overall influence the effect size, your hypothesis, research questions, everything. Okay, so yes, there are many strategies to address diffusion and compensatory rivalry, depending upon what your study is about, study design, so on and so forth. One thing which, as I said, which in my practical example was cluster randomized control trial. Okay, so now you have aptitude treatment interaction. So what does this mean? It means that this is an example which I covered, that sometimes the sample which is studied, they have such unique characteristics that this may limit the generalization of the findings. Okay, meaning I have studied Indian mothers in Australia. I cannot say that my questionnaire is applicable for all mothers living in Australia, irrespective of their ethnicity, and this questionnaire is going to work for all population groups. No, that is absolutely wrong. I can't really do anything about it. My study was to investigate feeding practices of Indian mothers. I just have to acknowledge that this questionnaire is made for Indian mothers. It has limited external validity. To have external validity, you will have to actually run the same study in another ethnic group and see whether it's working or not, or if there are any modifications required. All right, then you have your Pygmalion effect or Rosenthal effect. So what is this? This is, it means that greater the expectation upon the participants, the better they will do. So what does this mean? It means that this is seen a lot in experimental studies, guys. When, for example, when you call children into a lab setting or adults into a lab setting, because they are in this unique scientific, sciencey food lab environment, they act really different, and they are not showing behaviors which is part of their regular daily lifestyle. All right, this has also happened. So let me share this example with you. So this has also happened when I was doing my postdoc at Emory University. So Emory is in Atlanta, Georgia. So over there, we were, say, dealing with, these teenage children, and these teenage children had genetic metabolic disorders such as phenylketonuria, and we had to take their dietary recall, like what have they eaten in the past 24 hours and things like that. And these children, these children knew that we are researchers, we are coming from these big universities, and we want to do research with them and stuff like that. They got so overwhelmed, and a lot of PKU children are quite naughty. Okay, they won't be following the ideal diet and stuff like that. But the kind of dietary recall they were giving was impeccable. You would be like, what intervention do we run on them when they have these perfectly amazing diets? But that was not the case, okay, because their moms, they gave us a dietary recall, and that was drastically different from the dietary recall we had with the children. And this was because of the Rosenthal effect, where the children got scared. They were overwhelmed with big researchers sitting in front of them. And that is why they wanted to look their best. And that's why basically they lied. Okay, so let's not sugarcoat it anymore. So yes, so this is these are conditions in which this is not good. What was the way around it? We had done data triangulation. What is data triangulation? We had the mom's dietary record. The child's one was quite faulty. The third one which we had was they came to something which is called as a metabolic camp. In metabolic camp, they are with us day and night for a week, and they have all the free foods available, and you would be observing them and things like that. And then from that observation, you can make a dietary recall to see what they are eating and what is their general dietary pattern like. Okay. So yes, we did a data triangulation collecting dietary data with 3 methods, and that's why we could show that method number say A and C were more say reflective of true diet, which is the one reported by the moms, and the one which we have observed as a researcher passively. Okay, not like sitting and breathing on their legs, not like that. Okay, so yeah, that's your Rosenthal effect. Then you have so this is just, guys, this is just to summarize the concept that the relationship between internal and external validity is quite challenging. Okay, depending upon, again, it's always you have conditions. Okay, depending upon your research question, hypothesis, study design, the relationship between internal and external validity can become quite challenging. So for example, if we have a randomized control trial, you have very good internal validity. Okay, why? Because in a randomized control trial, you can control for, you can manage a lot of other confounding variables which are troublemakers, and then you can show that because I have managed all of these confounding variables, it is my IV which is causing the BV. Okay, but the other side of randomized control trial is that because you're trying to control for and manage for so many confounding variables, this becomes quite experimental in nature, laboratory types in nature. It may not be reflective of the participants' real life, say day-to-day life, say practices and behaviors and strategies, and therefore it may have limited external validities. But mind you, that this is an example which I'm giving. There are many randomized control trials which have a good balance of internal and external validity. But yes, that is something which is different and not within the scope of this. On the other hand, for example, when you have studies which are done in completely naturalized settings, say no control whatsoever, more observational based or qualitative based, yes, then you have amazing external validity because you are say inquiring, interacting, and understanding the participants in their real life, say day-to-day life practices. Okay, so that is like a different scenario, okay, where you have good external validity. All right, so yes, which weightage to give, more internal validity or more external validity, depends upon your research question. For example, let me share this with you. It's a very obvious example. So in this example where I'm developing this amazing questionnaire, so in this study, my main intention was that my questionnaire should be perfect, should be supportive for the Indian mothers. My research question hypothesis was not going beyond Indian mothers. So so external validity was not a worry for me. It was a acknowledgement of a limitation. Okay, so I can acknowledge it as a limitation, but that's about it. My main focus was that I should have excellent internal validity to show that my questionnaire is working for Indian mothers in Australia. And that's why I have done all of these internal validity, all of these indices. Why? Because to show that my questionnaire is working for my population. For external validity, I have acknowledged it as a limitation, and that's about it. Future researchers can use my questionnaire if they wish to validate it within their population setting. Okay, so hope that makes sense. This is what I'm saying, that you can't achieve everything and anything which is out there. Anything which you do is all defined, and it is all underlined by your research question, hypothesis. What are you trying to study? Okay, it's similar to what I said as an epidemiology as a unit. Okay, meaning that you cannot apply all of these epidemiological concepts in that one magical research project. Okay, no. You will be able to apply one or two of this concept into your real life research project, depending upon what your research question is. Okay. So yes, that again say encourages me to tell you that if at all, if you want to do a PhD within the say nutrition space, do let me know, because I would be very happy to support you, supervise you, and talk more about your journey, your doctorate journey. Okay. So yes, do reach out if you are genuinely interested in doing a PhD. Okay, so guys, there are other threats to reliability and validity, and these are covered in the coming lecture as biases. I don't know why I have this one more S, but yeah, they are covered in the coming lectures as biases. Yeah, now I know why I have that S. Okay, all right. So yes, you will be learning more about biases. Now your biases are again increasing your threats to reliability and validity concepts, and you'll be learning more about them. Okay, so I guess that's about it. Yep, yeah, that's about it from my end, guys. So I hope this lecture has been meaningful, and I'll see you soon in your coming lecture. Oh, and your tutorials as well. All right, thank you, guys. Thank you.